Welcome back to the final episode of our Inside Time series Explainer. Over our journey together, we've watched algorithms completely evolve. We saw how moving averages remove noise. We watched autoregression learn from observations. We used ARIMA to handle trends, SARIMA for seasonality, Profit to simplify business forecasting, and LSTMs to introduce deep memory. But today, we are going to solve the ultimate mystery. Why is a completely different architecture, transformers, suddenly rewriting the rules and replacing decades of forecasting algorithms? Let's get right into it.
To break down this incredible paradigm shift, here is our agenda. We'll start with 1, beyond sequential memory, move to 2, teaching AI where to look, then 3, inside transformer forecasting, 4, at foundation model scale, and finally 5, the future of forecasting.
To truly appreciate where we're going, we really have to understand the brick wall that traditional models eventually hit. Just imagine trying to forecast electricity demand over 5 full years. Or picture monitoring thousands of IoT sensors simultaneously over decades. We really have to ask ourselves, if the sequential memory of previous models relies on squeezing information step by step through a single bottleneck, is that actually enough for massive complex systems? Can one single memory cell really remember everything?
Section 1. Beyond sequential memory.
For decades, the evolution of forecasting was strictly chronological. Way back in the 1970s, ARIMA came along and introduced robust statistical tracking. It was brilliant for linear patterns, but, it really struggled with high volatility. Then jump to 1997. LSTMs, or long short-term memory networks, brought deep learning into the mix. They use these clever gating mechanisms to capture complex, nonlinear dependencies by essentially remembering past mistakes. And they were super effective. We're talking up to an 87% error reduction compared to ARIMA on volatile datasets. But then, 2017 happened. Transformers emerged and brought a completely new philosophy. The architectural contrast here is just massive. See, while LSTMs were brilliant at capturing nonlinear patterns, their step-by-step nature became a huge bottleneck. They had to sequentially pass data through this constant error carousel. That meant training on massive datasets could literally take hours, and honestly, they still struggled to remember events from thousands of steps ago. So the stage was perfectly set for transformers, a model that processes data in parallel, looks at the global context, and completely skips those tedious sequential steps entirely.
Section 2. Teaching AI where to look. Let's build some intuition here without getting bogged down in equations. Think about this for a second. If I ask you a highly specific question about Chapter 12 of a textbook, do you go back and reread the entire book starting from page 1? Well, no, of course you don't. You instantly flip right to the most relevant chapters. And that simple idea brilliantly illustrates exactly how the attention mechanism allows AI to navigate massive time series data. It doesn't bother reading chronologically, it scans for relevance.
So instead of carefully carrying a fragile memory cell through time like an LSTM does, attention mathematically scores the relevance of every single past data point and analyzes the input sequence, calculates those attention scores, and highlights only the most relevant historical time steps. It can pull exact context from literally anywhere in the history to generate a prediction, whether that data point happened yesterday or 5 years ago.
And the absolutely crucial point here is this. The AI isn't just remembering anymore. It is actively deciding which historical variables are the absolute most important for the specific prediction it needs to make right at this exact moment. It dynamically weighs importance, which is the magic key that unlocks parallel computation and lets us train on massive datasets in a fraction of the time.
Section 3. Inside Transformer Forecasting.
Now, because transformers process everything all at once, they actually don't have a natural sense of time. To fix this, we have to inject positional encoding to explicitly tell the model the order of events. From there, they use a powerful encoder-decoder setup where the encoder processes a massive context window and the decoder generates the future forecast. But here's the really clever part. To train them, we use causal masking. We literally hide future data during training so the model can't cheat by peeking ahead. It forces it to learn how to truly forecast. And as a huge bonus, if your dataset has gaps, you just mask them out. The transformer handles missing values naturally. This foundational setup quickly spawned highly specialized time series architectures engineered to handle extreme long-range dependencies. Models like Informer, Autoformer, PatchTST, and FedFormer, each optimizing speed, memory, and accuracy. These engineering advancements are pushing us away from the old, iterative, analyst-in-the-loop approach. Traditionally, analysts had to visually inspect forecasts, manually spot problems, and constantly tweak models like Profit or ARIMA. But with transformers, we're moving toward highly automated parallel processing systems that handle complex modeling and gargantuan datasets almost instantly, without needing a human to intervene at every single step.
But hey, let's pause for a quick hype check. Transformers are amazing, but they aren't flawless. They actually have quadratic compute and memory limits. Basically, that means the longer the time horizon you feed them, the exponentially heavier the computational cost gets. Plus, recent studies from the research community have shown that for some long-term forecasting tasks, surprisingly simple linear models actually outperform transformers. Why? Because that brilliant attention mechanism we just praised is what we call permutation invariant. Basically, it can occasionally jumble the strict mathematical ordering of continuous time points.
Section 4. At foundation model scale.
Despite those trade-offs, when we compare the numbers, the shift makes total sense. Traditional models like ARIMA are incredibly fast, training in just a minute on low data. Profit is also efficient, taking about 5 minutes, and it's fantastic for seasonality. Now, deep learning models like LSTMs drop error rates significantly, but they demand heavy compute and massive datasets, sometimes taking 30 minutes to hours just to train. This high data and compute barrier is exactly why pre-training transformers at a massive scale became the absolute next logical step. The thought was, instead of training a model from scratch every single time, what if we trained one giant model on everything?
And that exact idea gave birth to time series foundation models, like TimeGPT, Chronos, and Moirai. By pre-training on millions of diverse datasets, we're talking everything from wind power and renewable energy grids to global supply chains, financial markets, and even healthcare epidemic monitoring. These modern models can generalize across incredibly complex industries. They deliver what's called zero-shot forecasting. This means they can accurately predict your specific business data without ever needing to be explicitly trained on it locally. It's a real game changer.
The biggest takeaway here is this profound philosophical shift. We are officially moving away from training isolated local point models that just try to guess a single number for tomorrow's sales. Instead, we are adopting global probabilistic models. These vast neural networks learn the underlying representations from thousands of related time series, allowing them to output not just a single prediction, but the probabilistic uncertainty of the entire data ecosystem.
Section 5. The future of forecasting.
As our algorithms shift from simply plotting numbers on a chart to deeply understanding temporal logic and structural uncertainty, the lines between forecasting a problem and making an automated decision to solve it are really starting to blur. So, we have to ask one final question as we wrap up. What actually comes after forecasting?
Well, we're rapidly moving toward a future defined by things like multimodal forecasting, digital twins, and autonomous planning systems. Soon, AI won't just tell us what the supply chain or the energy grid might do next week. It will act as an agentic system, actively adjusting our infrastructure in real time to compensate for the very disruptions it just predicted.
Over the 11 episodes of this Explainer series, we've journeyed across the entire landscape of this discipline together. We started with simple moving averages just to remove noise. We moved to statistical models to handle trends, explored neural networks to capture memory, unpacked the absolute brilliance of attention mechanisms, and finally arrived at the cutting edge of foundation models. We have witnessed a fundamental shift in how machines interact with time.
And through all the complex math, the vanishing gradients, and the deep learning architectures we've explored, it all brilliantly illustrates the ultimate truth of our discipline. Forecasting was never about predicting the future with perfect certainty. It has always been about making better decisions under uncertainty.
We build these models not to possess a crystal ball, but because, while the future cannot be known, with the right models, it absolutely can be understood. Thank you so much for joining me on this incredible journey. Our Explainer series may be ending, but the true era of AI forecasting is really just getting started.